All right. Many things to talk about. Where to begin? We have, so we talked about area last time I saw you all. We should probably talk about average value just a little bit. And there's a whole bunch of like biology applications that he's talked about. And then starting to talk about volume. Okay. Yeah, okay, cool. Let me fix this. Let's see. Let's do this. There we go. Let's do. So the thing I'll say about average value is it's actually really straightforward. So Co-17B, today is whatever day it is, it's fourth. So if you know how to find the area under a curve, you know how to find the average value. It's just simply taking the area you found and dividing that area by the length of interval of integration. So for example, we want to find the average value of, say, the function f of x equal to 3x squared on the interval from 1 to 3. We'll draw it in a second here, but the calculation is super straightforward. The calculation is going to be, well, average value is equal to 1 divided by 3 minus 1. We're essentially dividing by the length of the interval, and then we're integrating from 1 to 3 the function that we're finding the average value of. And this example I've picked to be really straightforward. So that's going to be 1/2 times the integral of 3x squared. So that's going to be x cubed evaluated from 1 to 3. We plug in and we get 1/2 times 3 cubed minus 1 cubed, which is 1/2 of 27 minus 1. So we get an average value of 13. Sure, yeah. Sorry, I'm just looking at something. Yeah, totally. So the idea here is that we were to draw this. My drawing is not going to be perfect because, if I plug in 3 to 27, which is kind of large, but this function looks kind of like this. You grab a different color pen here. What it's really saying is that somewhere between 1 and 3, there's a height where this function has the average value. Or in other words, you kind of think of it like, you can think of this, think of this area here as like some volume of milk sloshing around in a glass, and like it's sloshed really high up, and then you stop moving it around and it settles back down to where all the milk is at the same height. That height, where the area, I know it's really volume, but okay, where the stuff underneath it is still the same amount of stuff, that height is the average height of the function. So in this case, that height would be 13. So this is like 1 right here. It's like 27 right here. 13 is about, actually, sorry, that's 3, not 1. Apologies. Maybe 13 is about right there. So what we're saying is, if all of it was at this height here, that area would be the same as the total area of the curve. Maybe my picture isn't displaying it perfectly here because sometimes I draw this a little bit wonky, but that's the idea, is that if you were to let all this area come down, it would fill in that over there. And again, yeah, so my picture probably isn't, I probably drew this a little too high. It probably should be a little bit lower, like maybe right about there instead. Sorry about that. So then you can imagine all this area right here filling in this missing spot right here. And that height of 13 will be the average height. And there's really not a lot more to say about it, right? The average height is just take your integral, divide your definite interval by the length of the interval. Question?
Like integrated with the substitution, and then you have to change the bounds.
Definitely, yes. So I should say for any of these things that are applications of integration, all of the methods of integration are still in play. So I could ask you to find the average height of a function that required a u sub or partial fractions or integration by parts or right? Like any method is totally within that. Let's look at one more thing about this, and then we'll look at one more example. So let's say there is one other theorem you mentioned, which is the mean value theorem for integrals, which just says the following. So the mean value theorem says that there's a place we can find where, so basically we can find, let me draw this one here. We can find the value of C between the endpoints of your interval where you get that average value. Or how it's written in the book is that somewhere the integral from, in this case, 1 to 3 of 3x squared dx is equal to some f of c multiplied by 3 minus 1. Or in other words, the area is equal to the base multiplied by the average height or the average value. Those words get interchanged. Average height, average value, same thing. So the mean value theorem says you can find this value C, and C has to be between, in this case, 1 and 3. That's what the mean value theorem says. The way you'd still find C is by dividing by that and then solving. So if we wanted to find C here, to find C, we could set our function 3, in this case, C squared, equal to the average value we just found, which was 13. And if you solve for C, you get C squared equal to 13 thirds. So C is going to equal, now I should be a little extra careful here. It's not plus or minus in this case, because since C has to be between 1 and 3, the only value we're looking for is C equal to the positive square root of 13 thirds. 13 thirds is just a little bit bigger than 12 thirds, which is 4. So C is just a little bit bigger than 2. Do I have a, no, I don't have a parenthesis up. So that's kind of the gist. Let's look at one more example just to kind of address your question about like if we had other methods of integration. So let's look at something like, I'm trying to make something up that's not too terrible here. So we want to say find the average value of, let's see here. Sure. The integral from 0 to 2 of x squared times the square root of 1 plus x cubed dx. That seems relatively reasonable. So I wrote this question poorly though. Let me, sorry, don't write this right down yet if you haven't already. So what I really should have said is find the average value of f of x equal to x squared times the square root of 1 plus x cubed on the interval from 0 to 2. Apologies. That's the way this question should be phrased. And this is not my answer, right? What am I missing from my answer? Right, the 1 over 2 minus 0. So my average value here, doesn't sound good, is equal to 1 divided by 2, or 1 divided by 2 minus 0, but okay, times the integral from 0 to 2 of x squared times squared 1 plus x cubed. But once you've written this down, you're not tied to these limits of integration, right? You just have to evaluate this thing in whichever way works the best for you. So we're going to say, well, cool. This is what I'm going to do a u substitution. I'm going to let u equal 1 plus x cubed, or du is 3x squared dx. 1/3 times du is equal to x squared times dx. So great. There's my 1/3 times du underlined in red. And there's my u in the square root. And you have a choice. You can either choose to change the limits of integration or not. I'm of the mind typically that you should change them. I will say you should change them unless it's an improper integral, and then I think it's easier not to change them personally because because changing an infinity is kind of dicey. Like if your limit is infinity and you're saying like u is your limit squared plus one, it's kind of weird. So I wouldn't do it. Yeah. Uh-huh. No, it does not. So this whole integral right now, that one half is there as is, and I'm not going to change it because I've changed these bounds, right? Changing these bounds shouldn't affect that one half out there. Yeah, so that's a good point. We don't do that. And then simplifying or rewriting this, we're going to get 1/2 times the integral of the square root of u times 1/3 du. And let's change our limits of integration. Our old limit was u, now, sorry, was 0, and u is equal to 1 plus 0 cubed, which is going to be 1. And our old limit was 2. Our new limit is going to be u equal to 1 plus 2 cubed, which is 9. Doing a little bit of rewriting, I would rewrite this as 1/6 multiplied by the integral from 1 to 9 of u to the 1/2 du. Integrate 1/2 times, so 1/6 times u to the 3/2 times 2/3, evaluated from 1 to 9. So end up getting, let's see, 1/9 multiplied by 9 to the 3/2 power minus 1 to the 3/2 power. That's 1/9 times, see, 9 to the 3/2 is 27 minus 1, so we get 26 divided by 9. So average value, not too big a deal. You just take the integral and divide by the length of the interval. What else is it about that? Oh, let's do one. So we can look at a word problem though. Yeah. Cool. You want to do that one or that one? I like that one. So here is a average value word problem, which is kind of a bit extra actually, but that's okay. So I'll point out this problem is similar to, but not exactly like 6.2 number 18, in case that's useful at all. There's a lot of words here. I'm going to try to not I'm going to write them all. So here's what we've got. For a fish that starts life with a length of 4 centimeters. So fish starts at a length of 4 centimeters and has a maximum length of 29 centimeters. Can't grow any longer than that. It's just not possible. The person's name, Von Bertalanffy, whatever, the growth model. We don't care about the names. That's not true. We do care about the names, but not really that much. The growth model predicts that the growth rate. So this is where it's really super important to make sure you read the words, because the word rate changes the entire meaning of what we're like if you miss the word rate, you're going to think it says something different. So the growth rate means the derivative of the growth. So the model predicts, sorry, I haven't written the word down yet. The growth rate, that's a word you should definitely focus on. The growth rate is 25e to the negative a. I'm going to put something in front of that, so leave yourself some space. 25e to the negative a centimeters per year. And we're going to say that that is L prime of A. I don't know why they choose to use A here instead of a more typical choice of T, but they did, right? They said A for age, essentially, instead of T for number of years. Seems a little silly to me, but whatever. Where A is the age. We want to find the average length of the fish over the first 5 years of its life. And this problem often throws people because there's like an extra step involved here that's not super duper clear. So I'll point out, note, the average length is going to be the integral from 0 to 5 of our length function. And then what do I have to divide by? Right, I have to divide by 5 or multiply by 1/5. I'll point out we don't know the length function yet. They didn't give us the length function, they gave us the derivative of the length function. So before we can do this, we have to integrate our derivative to find the length function, which I feel like is a little confusing. For like this problem, I feel people miss that piece often. So first, we're going to find L of A is going to be the antiderivative of just, oh, that's interesting. Yeah, sure. Sorry, I just noticed that. Yeah. Yeah. Right. Cool. Yeah. So L of A is going to be the antiderivative of our L prime of A, which is going to be the antiderivative of 25 e to the negative A, yeah, which isn't too terrible to integrate. It's just going to be negative 25 e to the negative A plus C, right? It's not a definite integral, it's an indefinite integral. We're just finding the function. And then we can say that, well, we know that at time 0, the length of the fish is 4 centimeters. So we know that L of 0 is equal to negative 25 e to the 0 plus C, but that should be equal to 4. And not super surprisingly here, this is negative 25 times 1. If we add that to the other side, we're going to get C equal to 29, which definitely does work with the fact that the maximum length of this fish is 29 centimeters, right? If you think about this function here, so I should say, if we think about our function now, where we're plugging in C equal to 29 right there, if you let this A number get larger and larger and larger, this e to the negative A is going to get closer and closer to 0, and the length of the fish is going to get closer and closer and closer to 29. Okay, so now let's find the average value, or the average length. So the average length is just going to be 1/5 the integral from 0 to 5 of this thing we just found. Negative 25 e to the negative A plus 29, which we can totally calculate. That's going to be 1/5 times, let's see. The integral of negative 25 e to the negative A is positive 25 e to the negative A. And the integral of 29 is 29A. And then we're going to plug in our endpoints, 0 to 5. So we plug in 5, we get this 1/5 is just going to hang out. 25 e to the negative 5th plus 29 times 5 minus, plug in 0, 25 e to the 0 is 25, and 29 times 0 is 0. And you could simplify this as much or as little as you want. If you do simplify this fully, you get approximately, well, let's do one more step here. You get 1/5 times 25 e to the negative 5th. I'll point out that this part here is very small. Right? E to the negative 5th is 1 over e to the positive 5th, which is somewhere around like 200 probably. Probably more actually. And then you have 29 times 5, which is 145 minus 25, which is 120. And then this is approximately equal to 24.03. I'll point out that 120 divided by 5 is 24. So this part here is not contributing very much at all at the end of the day. So if you see that kind of problem, just be aware, right? If they give you a rate of change before you can find the average value, you first have to find the function by integrating. Okay, so what's up next? Yeah, what is up next? Probably, yeah. Yeah, let's do that. So let's go ahead and talk about some further applications of biology, and actually have a handout for all of you. Welcome. Try and pay you too. I could just pay all of you. Alright, there should be enough. Alright. So, I'm not sure. I'm not 100% sure if Dr. Adele expects you all to memorize these formulas. My bet is no, but it's hard to know for sure. So let's go ahead and look at some of these problems. Let's start with this first one, survival and renewal model. And so I think you talked about this in class briefly. Most of this is just knowing this formula or being given this formula, and then making sure that we understand the components of the problem that we put into each place. So here's the general setup. A population begins with some number of members, which you call P naught. And members are added at a rate given by the renewal function, which is R of T, where T is typically measured in years. Proportion of the population that remains after T years is given by the survival function, S of lowercase t. And it is important to note that lowercase t is a variable here. Capital T is just a number that we're going to write in the number for capital T. Then the population in capital T years is given by this formula. P of capital T equals S of capital T times the initial population plus the integral from 0 to whatever capital T is of S of capital T minus lowercase t times R of T times T, which is kind of a lot to memorize. I never thought I'd be able to, but after teaching this for a few years, I think I know it if I didn't have it in front of my face. But again, you should really ask or find out if he expects you to memorize that formula. My guess is no, but I don't know. So let's look at this first question. A population of insects currently numbers 22,500. And I think it's good when you're reading these questions to write down the information as we go. So I am saying that my P naught, my initial population of insects, is 22,500. It's increasing at a rate of, oh, they even gave us the name there, R of T equal to 1,225 times e to the 0.14 t insects per week. So in this case, time is measured in weeks instead of years. That's totally fine. I will also point out sometimes R of T doesn't actually have any T's in it. Sometimes R of T can just be a constant growth rate. So if the survival function for the insects is ST equal to negative 0.2 T, so I'm write down two things. I write down that S of T is equal to e to the negative 0.2 T. I'll write down something else in just a second. Where T is measured in weeks, how many insects are there after 12 weeks? So my capital T is 12. And I like to write down that S of 12 minus T, right? Because that's what we actually are going to need to put in up here. That's going to be e to the negative 0.2 times 12 minus T. And it might help to simplify that as e to the, let's see, 0.2 times 12 is 2.4. So that's going to be negative 2.4. And then negative 0.2 times negative t is positive 0.2 t. And I actually want to break that off as a different piece, like that. That's going to be the easiest way to put that into my integral and then kind of pull out the parts I don't need. All right, so there's all the things we have. Now we're going to write down our, what do you call this? Our population, our survival and renewal. I don't even know the name for this thing, the right name. Our population at time t. So we're going to say, great. The population after 12 weeks should equal S of 12. So I'm just going to plug in 12 for T there and get e to the negative 0.2 times 12, which I guess I could have simplified, multiplied by my P naught, which is 22,500. I probably should have left myself a little bit more room here. I'll write it down below instead. Plus the integral from 0 to 12 of my S of T minus T, which is e to the negative 2.4 times e to the 0.2 t, multiplied by R of T, which is e to the, where'd it go? Oh, sorry, 1,225 times e to the 0.14 t. Oops, that t is up there. Okay, so we're going to simplify a little bit. So a couple things I would do. First, I'm going to simplify this first part here. That is e to the negative 2.4 times 22,500. So I probably have 22,500 multiplied by e to the negative 2.4. And then over here we have plus, I'm going to pull out all my constants. So the 1,225 and the e to the negative 2.4, those both can come out in front. So I have 1,225 e to the negative 2.4 times the integral from 0 to 12. And let's actually combine these together. 0.2t and 0.14t, I can add those exponents together and have e to the 3.4, sorry, 0.34t. That's terrible, James. Sorry about that. Gross. Sorry, that looks terrible. I'm ashamed of my writing there. Yeah. So then we're going to integrate. We know how to integrate e to the something times t. So we're going to get 22,500 e to the negative 2.4 plus 1,225 e to the negative 2.4 times the integral of e to the 0.34t is going to be e to the 0.34t divided by 0.34, evaluated from 0 to 12. Plugging that in, we end up getting 22,500 e to the negative 2.4 plus 1,225 e to the negative 2.4 multiplied by, so let's just do the math here. You're going to get e to the, let's see, 0.34 times 12 is something. It's 3.4 plus 0.68, which is 4.08 divided by 0.34 minus e to the 0, which is 1 divided by 0.34. Let's see, let's make sure that looks right. Yep, it does. So that's our final answer without a calculator. If you use a calculator, you're going to get approximately 21,046. What does this mean? What we're saying is we started off with this many insects, 22,500. They are increasing at this rate of 1,225 e to the 0.4 times t. And the number that are surviving is this amount here. So we're kind of saying that as time goes on over these 12 weeks, some are going to die, some are going to live, we're going to make more of them. And at the end of those 12 weeks, this is how many we're going to have. So we decreased a little bit in this case, but you could end up with more or less depending on what your survival and renewal rates are. In my opinion, most of these survival and renewal problems are just reading the problem, parsing out what is what, tossing it into this formula, doing some integration, which can be kind of a pain. Like sometimes the integrals are more difficult than this, and then doing it, right? There's not much more to it. It's a somewhat difficult plug and chug, but it's very base level. It's a plug and chug kind of problem. You find the pieces you need to put in, you put them in the right spots, you do the things, probably some integration, and then you get a final answer. Questions about this? Before we look at something else. All right, let's look at the next page. On the next page, we have not what I thought I had over here. All right, we can do this one too. So let's read the question and see what we have. The city currently has 36,000 residents and is adding new residents steadily at the rate of 1,600 per year. If the proportion of residents that remain after t years is given by S of t equal to 1 over t plus 1, what is the population of the city 7 years from now? So this certainly has all the hallmarks of a survival and renewal problem. We were given an initial population, which was 36,000. We were given a rate of a renewal rate. They didn't say R of t, but they said the words adding new residents at a rate of 1,600 per year. So in this case, R of t is just 1,600, right? There's no t to plug in there. And then we're given a survival rate of 1 over t plus 1. And then we're given a capital T of 7 years. So then if we're going to throw this all into the formula, which is that P of capital T is equal to S of capital T times P naught plus the integral from 0 to capital T of S of capital T minus lowercase t times R of t dt. Plug in all the things. So P of 7 is going to equal S of 7 which is going to be 1 over 7 plus 1. That's our S of 7. Times P naught, which is 36,000. Plus the integral from 0 to 7. This is the one that always, I feel like people have a somewhat hard time. S of t minus t is going to be S of 7 minus little t, which is going to be 1 over 7 minus little t plus 1. That's going to be 8 minus t in the denominator there. So we have a 1 over 8 minus t. That's a t, not a 2. Times r of t, which was 1600 dt. It's my S of 7 minus t. Yeah. So when I plugged in 7 minus t, right? That's my capital T minus my lowercase t. I got 1 over 7 minus t plus 1. Because I'm replacing this t here with 7 minus t, but then the 7 plus the 1 I can call 8. So I'm just simplifying it to make it a little bit less cumbersome to write it all out. Okay. So then we get 36,000 divided by 8, which is, I don't know, what, something, 18,000, 9,000, 4,500. Plus, I'm going to bring this 1,600 out. And the integral of 1 over 8 minus t is something we should be able to do without a u sub. It's going to be the negative natural log of absolute value of 8 minus t. So it's going to be times the negative natural log of the absolute value of 8 minus t, evaluated from 0 to 7. Equal to 4,500. So let's bring that minus sign out in front. Minus 1,600 times the natural log of 1 minus the natural log of 8. So I end up getting 4,500 plus 1,600 natural log of 8. Whatever that ends up being. Oh, I forgot about that. Pass on the attendance form before I forget about it. Okay. So survival renewal, again, really just kind of plug and chug. You're finding the pieces, you're putting in the right spots, doing the whole thing. Questions about that before we move on to, I believe, a different style of problem. We can always be more. Let's look at this next thing, which I feel like again. I feel like I want to skip. So let's skip this one. So I'll say this one is another survival renewal problem. I think it'd be good for you to try on your own at some point. And I believe I have solutions somewhere which I can and will post. Let's skip this one for now and look at the next part. So cardiac output. There's a lot to read here. We don't need to read all of this, but I want to actually point out Dr. Liddell did make a small error when he was talking about cardiac output in class yesterday. Did he mention that he made an error? So when he was writing the formula for cardiac output, right, he had this F on the wrong side of the equation. He had it as A times F equal to the integral. He still had the right end equation, but you might have caught that there was an error in like, why, how is he going from this to that? And so, right, so we should have had that A, which is like the amount of dye. So like, I'll be honest, the biology here isn't super extracurricular to me because biology's not my thing. You've got like, we could read this if you want to. You're doing blood is going through the veins, enters the atrium, pumped to the lungs, to the arteries, blah, 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 flows back into the atrium through the veins, and then out to the rest of the body. The cardiac output of the heart is the volume of blood pumped by the heart per unit time. That is the rate of flow into the aorta. Cool. The dye dilution method is used to measure the cardiac output. We inject dye into the right atrium and it flows to the heart into the aorta. A probe inserted in the aorta measures the concentration of the dye leaving the heart at equally spaced time over a time interval until the dye has cleared. So it's again this idea of measuring things equally spaced times, taking that measurement, multiplying it by the change in time to approximate this integral, and then using an integral instead to kind of calculate it. So if we let C of t be the concentration by anytime t, and we divide this into subintervals, we can say that the concentration of dye multiplied by the volume of blood, which is the concentration times the flow that we're trying to determine, we get that the total amount of dye is given by concentration times flow times change in time, plus concentration times flow times change in time, right? It's all these concentrations times the flow times how much time has elapsed. We add those all together, we get an integral kind of thing, so that the amount of dye is equal to the integral of C of t times F times dt. Or we're just taking this and that and that. And then since that capital F is a constant, we can pull it out in front of the whole integral. So then you have that the amount of dye is equal to the flow, right? It's flow, yeah, flow, multiplied by this integral. And then to solve for the flow, we divide both sides by the integral and get that the flow is equal to the amount of dye A divided by the integral of the concentration, which is the end formula he did have, but he had this up on the wrong side. So in case you were curious about that, that's what was happening there. Just made a little mistake, which is totally fine. You make mistakes all the time. So these problems always, I find them vexing. They're just not my thing. Like I'm always like, what do we do here? I don't know. So let's figure it out together. So, and do I have something over here? Yes, cool. All right. Let's see what we've got. The dye dilution method is used to measure cardiac output with 6 milligrams of dye. Cool. So I think A is equal to 6, right? It's the amount of dye. The dye concentration in milligrams per liter concentrations are modeled by C of t equal to 20 t e to the negative 0.6 t. And time is between 0 and 10. So my 10 there is my capital T, if you like. Find the cardiac output. Okay. Sure. So the cardiac output is given by F equal to 6 divided by the integral from 0 to 10 of 20 t e to the negative 0.6 t dt. Okay. Have we over here? 1 second. Sorry, I can't move papers apparently. I don't know. Okay. So let's grab a piece of paper over here. Try to keep things in order. Really, we just have to find the integral and then divide the result, or divide 6 by the result. So let's just do the integral on its own. So this is number 11 from the handout. So we're going to have here is that the integral from 0 to 10 of 20 t e to the negative 0.6 t dt, we're going to have to use integration by parts here, right? So we're going to let, you can make a choice of either letting u equal 20 times t or just t and bring the 20 out in front. Let's do it like letting u equal 20 times t. So there's my u, there's my dv. So u is equal to 20t, dv is equal to e to the negative 0.6 t dt, du is equal to 20 times dt, and v is equal to e to the negative 0.6 t divided by negative 0.6. So we're going to do the whole integral. So this is going to end up equaling, so we have u times v, so we have 20t times e to the negative 0.6 t divided by negative 0.6. Evaluated from 0 to 10. This is not my favorite way to do it, but I kind of got here and didn't feel like going the other way. So usually I would just do the antiderivative and then do the limits of integration at the end, but it's also fine to write it this way. Minus the integral of v du, which is e to the negative 0.6 t divided by negative 0.6 times 20 dt from 0 to 10. Questions? Just my usual ultraviolet super voodoo. U times v minus the integral of v times du. Okay, I'm going to do a little bit of do I really want to simplify? Not really. I'm going to do, I don't know. I don't love this problem, as you might have gathered. That's fine. So let's go ahead and just keep this as is. We have 20 t e to the negative 0.6 t divided by negative 0.6. from 0 to 10. And if we integrate this here, we're going to have, so this minus and minus becomes a plus. So we have 20 divided by 0.6. But then when we integrate e to the negative 0.6t, we're going to get division by another negative 0.6. So we're actually going to get minus 20 divided by 0.6 squared e to the negative 0.6t. Just to walk you through that again, in case it wasn't clear, this is a minus, so it became a plus, but then the integral of e to the negative 0.6t gave us a division by another negative 0.6. So it ended up being negative overall. So you have negative 20 divided by 0.6 divided by another 0.6 times e to the negative 0.6t, 0 to 10. Okay, and then we plug in and we get gross numbers. We have 20 times, so I'm just plugging in my 10 here. I get 200 e to the negative 6 divided by negative 0.6 minus 0. Cool. And then plugging in here, I get, plugging in 20, I get, sorry, plugging in 10, I get 20 divided by 0.6 squared e to the negative 6 minus plugging in 0, I get 20 divided by 0.6 squared times e to the 0, which is 1. That's kind of gross. Yeah. And if you pull out a calculator, this is approximately 54.58. Which is not our final answer, because our final answer is that the cardiac output is 6 divided by the integral. So this is going to be approximately 6 divided by 54.58, which is approximately equal to 0.11. What are the units? Let's see here. So this A here, this amount of dye is 6 milligrams. And the concentration is milligrams per liter. But we're integrating with respect to time, which is kind of like multiplying by a unit of time. So what we really kind of have here is milligrams per liter times unit of time, which is measured in seconds. The milligrams cancel, the liters come up to the top, and you get liters per second, which would make sense for the cardiac output being a measurement of flow, right? It's a volume per unit of time. So approximately 0.11 liters per second. Not my favorite type of problem, but the calculation, so even though the integral is gross, the thing you're calculating is not that hard. You just have to know that it's the amount of dye divided by the integral of the concentration, which I will freely admit, I never remember. It's always like, what do we divide by what again? I don't know. But it's not too hard to do once you figure it out, typically. See if there's any other interesting things over here. I can skip this next one, this handout, because I feel like there's one of the one I want to get to. This one's more of an estimation one also. Yeah, let's look at this last thing here, which is Poussin's law, which he definitely did talk about in class as well. Let's look through it here. I feel like I'm missing something. Okay. So this equation, F equal to pi times P times R to the 4th over 8 eta L, is called Poussin's law. It's about how things flow through like a vein, I think, and how basically the idea basically is that towards the middle of the vein, things flow faster. Towards the ends of the vein, things flow slower because like there's more, I don't know, friction maybe. I don't know. I'm not a biologist. I'm a math person. So I know what the equations are saying. Let's read through the question. Poussin's law, it shows that the flux is proportional to the 4th power of the radius of the blood vessel. So the bigger the radius, the bigger the flux. Okay. I'll point out, right, like everything else here is a constant. Right, pi is a constant, P is a constant, eta is a constant, eta is a constant, L is a constant, or at least it's a measurement of like how long we're traversing. So There's really only one thing going on here. Maybe P isn't a constant. What is P? Let's find out. High blood pressure results from constant. Oh, P is the blood pressure. So high blood pressure results from constriction of the arteries. To maintain a normal flow rate, aka flux, the heart has to pump harder, thus increasing the blood pressure. It's kind of neat. Like you never really think about like when they're measuring your blood pressure, like what they're. I mean, you kind of think about it, but like maybe not as much as the Poussey was thinking about it. Use this law to show that if R naught and P naught are normal values of the radius, and pressure is an artery, and pressure in an artery, and the constrictive values. Let me say that again. I feel like I paused weirdly there. Show that if R naught and P naught are normal values of the radius and pressure in an artery, and the constrictive values are R and P, then for the flux to remain constant, P and R, pressure and radius, are related by this equation. So this is a pretty typical question. I feel like everyone always asks this question. You might see this, you might have already seen it. Still worth looking at. So all we're really going to do is take this equation up here and try to manipulate it. So here's what we know that needs to be true. We want the flux to remain constant, whether we have the original values of pressure and radius or the constricted values of pressure and radius. So what we're really saying here is that whether you have the regular values for flux, I'll just use regular F, or the constricted values, let's call that F naught using the P naught and the R naught, those should be equal to each other. So that means that our F, which again, you can't see the equation. Well, you can see, you'll have the paper in front of you. Your F, which is the pi times whatever, is going to be pi times P times R to the fourth over 8 eta L. And that's going to equal F naught, which is pi times P naught times R naught to the fourth over 8 eta L. And as you might guess, most of these constants are just going to cancel. You can divide both sides by pi, you can multiply both sides by 8, you can multiply both sides by eta, you can multiply both sides by L, because all those things are the same on both sides of this equation. So just simplifying a little bit, the first step, this reduces to P times R to the fourth equals P naught times R naught to the fourth. And I bet we can get from here to there pretty quickly. Divide both sides by P naught. So P divided by P naught times R to the fourth equals R naught to the fourth. Divide both sides by R to the fourth. So P divided by P naught is equal to R naught divided by R, all to the fourth power. And that's exactly what we wanted. Not much to do, really. The second question is a little more interesting, I think. Deduce that if the radius of an artery is reduced to 3/4 its former value, then the pressure is more than triple. Do I have enough room here? Maybe. So, remembering, or at least using the notation we've already used, R naught is the original radius and R is the new radius. So let's say, great, let R, the new radius, be reduced to 3/4 of the original radius. So the new radius is equal to 3/4 of the original radius. And let's plug that in to this equation. What that means then is that the new pressure divided by the original pressure is going to equal, which way do I want to go here? Good question. Which way do I want to go? Doesn't really matter. So it might be, so I was going to plug in 3. Yeah, it's fine. Yeah, sure. R naught divided by 3/4 times R naught to the fourth power. And what can I cancel right off the bat? What can I cancel right off the bat? Yeah. So then you have 1 divided by 3/4, which is 4/3. So you have 4/3 to the fourth power. And 4 to the fourth is 256. And 3 to the fourth is 81. Sorry, 256. And that number is bigger than 3. Right? 256 divided by 81 is a little bit bigger than 243 divided by 81, which is equal to 3. This is bigger than 3, which means that P divided by P naught is bigger than 3, or multiplying both sides by P naught, that the new pressure is more than 3 times as big as the original pressure. So constricting that radius, not a lot, right? I mean, a lot for like, your blood vessels are not very large, but constricting it to 3/4 its original size means you have more than tripled the blood pressure, assuming that this equation is true. That's a lot of blood pressure. That's not good for you. So make sure those radii of I don't know how you make sure your blood vessel radii stay large, probably by exercise, right? Cardiovascular health, but seems like it's important. All right. I think that's enough of those. So again, this handout, I'll make sure that I find and or write solutions to the other problems so they can be posted on Canvas. But I feel like that's enough of that. He definitely does. Like, so I was working on writing up a second practice midterm, and there definitely are questions about Bussey's law on there. I feel like, and survival and renewal, both of those were definitely on the practice midterm. And I'm trying to remember, I think he gave the formulas for them, so I wouldn't sweat too much knowing the formulas. Definitely knowing how to use them is important. All right. Cool. Make sure there's nothing else here I really need to say. What time is it? Okay, it's 11:20. We got a half hour still. Okay. Oh, I do like this question. But fine. Yeah. Okay, we'll do this question too. We'll do one more. No, we won't. I'll save this for later. This is a better question for later. Let's talk about volume. Get my notes in order. They're very out of order. Sorry. Talked about volume a little bit yesterday, right? Not a lot, but a little. And we kind of went this other direction first. All right, there's particular notes I'm looking for that I really want. Fine. Okay, so there's kind of two ways we talk about volumes in this class. So volumes of solids. And the first way he did class today is what I kind of think of as the annoying way, the less enjoyable, not as fun way. That's kind of weird. Let's see if I can. I'm trying to find my examples right there. 1 second, please. No, not you, but you're for later. Here we go. Yes. Okay, let's look at these examples first. The first example he did was talking about finding the volume of a sphere, doing this kind of weird thing where you look at slices that are circles. And he did the second way where you took like the area of half of a circle and rotated it around. That's the more nice way of doing things, in my opinion. But there are some shapes that we don't do that for. So here's another example, not to just repeat the example he gave. So here we go. The base of a solid, these are usually how they start, is by talking about the base of your three-dimensional shape. S is a circular disk of radius. Let's actually pick a real number. Let's say radius 6, lying on the XY plane. Or as I like to think about it, you've got a circle on the floor. Cross sections perpendicular to the x-axis I should say cross-sectional areas that are perpendicular to the x-axis are thin square slabs. Find the volume. We're gonna draw a picture first. I wish I had a device. So the idea basically is on the floor, there's a circle, and then depending on which part of the circle you're at, you've got a square popping up out of it that's either bigger if you're in the middle or smaller if you're near the edge. I'll try to draw it, but well, you know what? I won't try to draw it. I'll just show you this nice picture that someone else has already drawn. Here's a nice picture of what's going on. So we've got our circle that's on the floor. This is the top view. And you've got your slices that are squares, again, looking at it from the top. And then here's the side view. There's your circle that's on the floor. And in the middle, you have bigger squares because you're slicing perpendicularly to the x-axis, and then closer to the edge of the circle, you have smaller squares. That's the idea of this shape. So then the question becomes, well, how do we find the area? Well, kind of like before when we found, or sorry, back it up a little bit. Question is, how do we find the volume? And we're gonna do it kind of like we did before when we were finding area. We're gonna add up all the areas of the rectangles. But now we're gonna add up all the volumes of the squares. And as you might notice, not every square has the same volume. The ones near the edge have less volume, the ones in the middle have more volume. So just like when you're integrating a function, the area of your rectangle depends on the function that it's under. Similarly here, the volume of the slab or the square is going to depend on the function that it's, in this case, over actually, or the bounds of it. So here's how we're going to do this. So we're going to draw our circle here. And we're going to draw a little representative slice right here. So here's my little slice. And before I think about the square popping up out of it, I'm going to think of, well, I need really to know what the length of that little strip is. I need to know that length. Because then the area of my square is going to be that length squared. And the volume of my slice, or my slab, whatever word you like to use, the volume of my slab is going to be that length squared multiplied by a small change in x, which is dx. That's a small change in x right there. Okay, so again, if you want to, I don't think you need to, but you can draw like, oh yeah, there's this square that's like coming out like that. It's kind of draw, but also not really. There's my square. It's popping up out of this circle. So we need to find the equation for that, right? Because if we're gonna find the total volume, right? The total volume, we're going to be doing the integral from, oh, what's the radius of the circle again? It's 6. So we're going to be doing the integral from as far left as -6 to as far right as +6 of that length squared times dx. But to be able to actually integrate it, we need that length to be a function of x. So we're going to find that length as a function of x by thinking about the equation of this circle. Okay, well, the equation of our circle is x squared plus y squared equals the radius squared, which is 6 squared. So the top half of the circle is y equal to, well, let's use it to solve for it. So we've got y squared equal to 36 minus x squared. So the top half is y equal to the positive square root of 36 minus x squared. And the bottom half is y equal to the negative square root of 36 minus x squared. So bottom half, y equal to the negative square root of 36 minus x squared. Top half, y equal to the positive square root of 36 minus x squared. And the length of that strip is the top function minus the bottom function. So my length here is going to be the square root of 36 minus x squared minus the negative square root of 36 minus x squared, which is just going to be 2 times the square root of 36 minus x squared. And that is what our length is. So that's what's going to get plugged in right there. Now, the nice thing about most of these problems, most of the time, is the ugly thing you have over here, which is usually a square root of something, often ends up getting squared. So it ends up being relatively not terrible. So here, our volume is going to be the integral from -6 to 6 of 2 times the square root of 36 minus x squared quantity squared dx. We square it out. Each part gets squared, so the 2 gets squared. That's a 4. So we have 4 times the integral from -6 to 6 of the square root of 36 minus x squared is 36 minus x squared. And then the rest is a really straightforward definite integral. We get 4 times the integral of 36 is 36x minus x cubed over 3, evaluating from -6 to 6. We plug in and we get 4 times the 36 times 6 is 216. 6 cubed is also 216. Minus the negative of that, so negative 216 plus 216 over 3. And that's something. 216 divided by 3 is 72. 216 minus 72 is 144. So you get 144 plus 144, 288 times 4. Sure. 4 times 288, which is another number. Sure, you all could tell me. I'm gonna leave it as that because I don't feel like. But the point, again, the point is not to do this, right? The point is to understand how to set this up. So these slicey ones can be moderately terrible to very terrible, depending on the base shape, whether it's a circle or a part of a parabola or something else, and then what the shape that's popping up out of it is. And your options are typically a square, semicircle, a full circle, an equilateral triangle, which is kind of the worst, or a right triangle whose like hypotenuse is the base. So right, which we'll do, because I think that one's kind of the most interesting. So let's look at another example, and then we'll move on to the more typical volume questions. So okay, let me try to make sure I don't make up an interval that's too terrible. But let's go here. So let's say we've got the following. Yeah. So the base of a solid is a parabola. Or I should say, parabola. That's not right. The base of a solid S is bounded by, as I should say. Apologies. Sorry, this is what happens when you make a problem on the fly. Is bounded by y equal to 0 and y equal to 9 minus x squared. So it's the region that looks like this. We got intercepts at 3, 0, negative 3, 0, and 0 coming up. Cross sections perpendicular to, and it doesn't matter what axis we are perpendicular to, perpendicular to the y-axis are right triangles whose hypotenuse lies in the xy plane. So the idea basically is my slab, my cross section looks like a right triangle where the hypotenuse is the side that's sitting on the ground, essentially. So like that's my little slabby piece right there. Kind of make sense? So let me kind of make more sense. So this is my length L here, perpendicular to the y-axis. This length L is the same as this length L here. That's the idea. So we're gonna have a bunch of, so if I tried to draw the three-dimensional shape here, so check this out. I'm gonna try to draw it. These always go so here's my XY axis kind of drawn so it's flat, and then popping up out of my XY axis are little slabs that are right triangles. Seem plausible? Maybe, I don't know. Questions? Okay, let's talk about the area of this shape. So we have to do two things. We have to find I should say volume. We have to find the volume of our slab. And then we also have to find the length of L. You can do either one first. It doesn't really matter. Let's find the volume of the slab. So, okay, right triangle. If I know that the hypotenuse is L, I can certainly find these other two sides here. Let's call them, I don't want to use X or Y. Let's call them A. Do I really need to find those other two sides? I'm just trying to find the area of the shape. Yeah, I guess I do. Right, because the area here is going to be A squared times a half, right? 1/2 base times height. So let's see. So we have A squared plus A squared equal to L squared. So 2A squared equals L squared. So if the volume of the slab is 1/2 times A times A times dy in this case, I guess, right? Because it's a small change in y, then A squared is equal to 1/2 L squared. So that's going to be 1/4 L squared dy. I admit this feels a little confusing. Because I'm trying to say, I'm gonna find this length in terms of what y is. So I'm trying to write the volume of this triangular slab in terms of what that length L is. And then in the next step, I'm gonna find L in terms of my variable y. So that I can actually integrate from a low of y equals 0 to a high of y equals 9. So let's find the length. All right, well, this equation here is y equal to 9 minus x squared, but the right-hand side, essentially I'm trying to find that xy and that xy and find the difference in the x's. So I have to find, well, the right side, if I have y equal to 9 minus x squared, then you have x squared equal to 9 minus y, and you're either going to get x equal to the positive square root of 9 minus y, or x equal to the negative square root of 9 minus y. This is the right side. This is the left side. So we want to do the right minus the left. My length is going to be the square root of 9 minus y minus a negative square root of 9 minus y, which again is going to be essentially 2 times your thing. So that's how long each strip is. Let's think about this for a second. So if we're down at a height of y equal to 0, down here. So first of all, just look at the picture for a second. If you're down at the bottom, how long is your strip? From -3 to 3. 6. If you plug in y equals 0, do you get a length of 6? You for sure do. 9 minus 0 is 9, square root of 9 is 3, 2 times 3 is 6. So it seems reasonable that this is actually the length of the hypotenuse of our right triangle. And if you go up higher, if you go all the way up to 9, you're going to get a length of 0, which, yeah, 9 minus 9 is 0, so it's a length of 0. So now finally, we're able to set up the integral. The volume is going to equal the integral from as low as y equals 0 to as high as y equals 9 of my 1/4 my length squared dy. That's going to be 1/4 my length, which is 2 times the square root of 9 minus y squared dy. And then the actual integration is going to be not terrible at all. The 1/4 is going to multiply by the 2 squared and actually cancel out. 1/4 times 4 is 1. And then you're going to have the integral from 0 to 9 of 9 minus y. It doesn't get a whole lot easier than that. Integrating, you get 9y minus y squared over 2 from 0 to 9. And plugging in 9, you get 81 minus 81 over 2. And plugging in 0, you get 0 minus 0. So you end up getting 81 over 2. So most of these weird base problems with a strip with like a solid popping up out of it with these weird slabs are kind of awful to set up, but the actual integration is usually like very nice. Okay, let's talk about the more typical volume problems, or volumes of revolution. Oh yeah, question.
So when it comes to find the area or like
Volume, sorry.
yes, slabs are equilibrium, like triangle or
Well, so again, so these are not equilateral triangles. These are right triangles whose hypotenuse is the base. But if I had said equilateral triangles instead, it's a much worse problem.
wait, I mean but I meant like so we would assume that the side lengths aside from the hypotenuse are always the same.
Yeah, because I said it's did I miss a word that I needed? I ran a word. Yeah, I guess I probably needed to include the word isosceles. Apologies. Yeah, cross sections are right isosceles triangles. Sorry about that. Yeah. So, thank you. Volumes of revolution, which typically boil down to what we call either the disk or washer method, which I will say are really the same method. One of them is just has an extra piece we consider, whereas the other one doesn't. And let's look at some typical examples here. All right, 1 second. I need to respond to a quick text message. Quick text message. Sorry. Okay, so a typical example of something like this would be to say, find the volume of the solid formed when the region bounded by y equals x cubed, y equals 0, and x equals 2 is revolved around we'll start with the x-axis. In this class, whichever axis you're revolving around tells you what variable you have to use. So if you're revolving around the x-axis, you have to use x's. Or I will point out, because I think the delta does like to extend this, if you're revolving around an axis that is parallel to the x-axis, you have to use x's. So for example, if I said revolve this around the line y equals -1, which is a horizontal line parallel to the x-axis, which is just the line y equals 0, we would still use x's. On the other hand, if we revolve this around the vertical line, like the y-axis, we have to use the y variable. So revolving around a horizontal axis, we use x's. Revolving around the vertical axis, we use y's. End of story. In other classes, not this class, but in other calculus series, they teach about another method called the shell method, where then you kind of switch the variable you use, but that's not something we're going to talk about. So if you've ever heard of the shell method, forget about it for this class. If you haven't, don't worry about it. It's not important. So we're just talking about the disk/washer method. So I think it's always a good idea to draw the region that we're revolving. So I'm going to draw, let's see. I've got y equals x cubed. I've got y equals 0. And I've got x equals 2. And the region we're talking about has to have all of our curves as boundaries. So it has to be this region right here. Sometimes it can be a little unclear, sometimes, especially if something's like next to the y-axis and you think, it could be that, but the y-axis isn't included, It's not the region. So make sure that whatever region you're looking at, it's going to be bounded by all of the curves that were mentioned. And then the idea here is we're going to draw a little strip or rectangle that is perpendicular to the axis of rotation. Must be perpendicular. You have no choice. Has to be perpendicular. So in this case, since we're revolving around the x-axis, my strip is going to be perpendicular to the axis of rotation. And the idea is that we're going to then rotate this region around the x-axis. And specifically, when we rotate this little strip, you're going to get a disc shape. Right? You're going to take this one thing and you're going to rotate it all the way around. And it's going to essentially draw out a disc. So I don't usually like to draw the whole thing, although like usually I think this is enough to draw. But if you think about what's going to happen here, we revolve that region. The way I typically draw it is I just draw kind of the outline of it. So I'm going to draw that part there. And then I'm going to mirror it down here. And then think about the 3D shape I would have gotten. And then specifically this little strip here gives me a little disc. Okay, so just like before, when we were finding area, we found the area of one rectangle and then we added up all the rectangles. Now to find the volume, we're going to find the volume of one of those discs, and then we're going to add up all the volumes of the discs. So the volume of that disc, well, the volume of a disc is the area of the circle multiplied by the thickness of the disc. The thickness is going to be dx. And the area of the circle is going to be pi times some radius squared. The radius depends, right? If you're closer to 0, the radius is small. If you're closer to 2, the radius is big. The radius is just how high that strip is, or the function. So in this case, we're going to get pi times x cubed squared dx. That's the volume of one disk located at x away from the origin. You don't really have to say the x part, but okay. And then to find the total volume, we're going to add them all up. So we're going to integrate from as far left as 0 to as far right as 2 of pi times x cubed squared dx. People typically pull the pi out in front. And then we have the interval from 0 to 2. X cubed squared is x to the 6th. Easy to anti-differentiate that. We get x to the 7th over 7 from 0 to 2. We plug in 2 and we get pi times 2 to the 7th, which is 128 divided by 7 minus 0. So we end up getting 128 pi divided by 7. We don't care about units unless someone mentions units specifically. So I would point out that when your region is flush with the axis of rotation, or another way to say it is there's no space between your region and the axis of rotation, or another way to say it is your axis of rotation, in this case the x-axis, the equation y equals 0, is one of your boundaries, we end up using the disk method because the shapes you get are disks when you rotate it around the axis of rotation. On the other hand, if we rotate this around the y-axis, then we have space. So let's actually take a look. Yeah, we have enough time. We go around the y-axis real quickly here. Same shape. Okay. But now we're rotating around the y-axis. So again, I'm going to draw my little strip perpendicular to the axis of rotation. There's my strip. And now you can see that when I rotate that around, I'm not going to get a disc shape because I'm going to be missing this whole middle part. So what's going to happen is I'm going to instead get this washer shape. That. Where the washer has a thickness of dy, And the volume of the washer is the area of the larger circle with a bigger radius minus the area of the smaller circle, the smaller radius, all multiplied by the thickness, d1. So if your region isn't flush with your axis of rotation, it's going to be the washer method. If your region is flush with the axis of rotation, it's going to be the disk method, but it's really just the washer method where the inner radius is 0. So I will say again, the disk method really is just the washer method, but the inner radius is 0, so it's easier. So that's why I say they're the same, because they really are the same, just one's slightly more complicated. So in this case, our outer radius is this curve here, which was x equal to 2. Our inner radius was the curve y equal to x cubed, but we can't be integrating with respect to x or with respect to y, so that has to become y to the 1/3 equal to x. So our total volume here is going to equal the integral from as low as y equals 0 to as high as y equals 8, because that point is 8 there, of pi times your larger radius squared minus pi times your smaller radius squared. We typically factor out the pi. We get pi times the integral from 0 to 8 of 4 minus y to the 2/3 power. And then you can integrate and get some final answer. Pi times what? 4y minus y to the 5/3 times 3/5 from 0 to 8. That's going to be pi times 4 times 8 is 32 minus 3/5 times 8 to the 3/5 is also 32, because it's the cube root of 8, which is 2. 2 to the 5th is 32. Minus 0, minus 0. Pro tip here, instead of multiplying out 3 times 32 over 5, recognize that you have 1 of 32 minus 3/5 of 32, so you're left with 2/5 of 32. So you have pi times 2/5 times 32, which is just 64 pi over 5. Which is not at all the same volume. It shouldn't be, right? This is a very different shape. Right, if you think about drawing this out, it would look kind of like this. And you kind of have like a, kind of like that. Kind of like if you took a cylinder. Oh, you know what it kind of makes you think of? Kind of makes you think of like a steel drum. Like how it's kind of bold in the middle. Like the steel drum wouldn't go very down to the very bottom there, but it's kind of like that. You've like taken this cylindrical shape and hollowed out this bowl part in the middle to have this volume left over. All right, we'll talk more about this stuff on Thursday. Try not to get too wet out there. It looks like the rain's actually stopped for a moment, so